Hello everyone, my name is Robert Schwan Reifert and I will take over now for the third part of our tutorial. Previously we have heard an introduction and an overview of the tutorial and talked about the overview of Cloud Radio Access Network provisioning. In this part of the tutorial we will talk about the multi-cloud radio access network over provisioning. In more details, that means we start by a motivation to go from the single cloud to multi-cloud perspective, as we can see on the right-hand figure. Then we also detail the architecture of this specific multi-cloud radio access network. Before then, we will go into the optimization problem of this section, which is an energy efficiency maximization, where we first also talk about two techniques, first of which is the generalized assignment problem, and second one is L0 normalization. Both are formulated and so used to solve the maximization problem. Then next in line, we talk about caching. So we bring caching into the multi-cloud radio access network, allow that at each base station, and check its impact on the energy efficiency. And specifically here, we also talk about fractional programming as a mechanism to solve the problem. At last, we talk about challenges and limitations of the multi-cloud radio access network. So, starting 2015, we have some reference works on the multi-cloud perspective, which are sometimes also done by us, reaching the recent years, 2022, where we also produced two works on the multi-cloud radio access networks. So first of all, let's talk about the transition from single to multi-cloud runs. On the right-hand side, we see a figure where we have some application, and this is served by multiple public clouds in this case. And now the transition from a single to a multi-cloud radio access network involves a shifting from a centralized and single cloud provider infrastructure to a more flexible and resilient architecture that leverages multiple cloud environments, as we can see, for example, on the right-hand side. By doing so, we are able to enhance the scalability, introduce redundancy in our system, and are able to improve on the performance metrics of this said system. This evolution actually, so the transition from single to multi-cloud, that allows operators to optimize resource allocation across each cloud platform. We can reduce the latency of the overall system and improve actually the service reliability. And this part of the tutorial, we will focus on the multi-cloud, so to say, multi-central computer, central processor run perspective with practical cooperation limits between the cloud environments. Okay, now we start with the architecture of the multi-cloud radio access network. So for us, we see that we have an exponential increase in devices and applications in 6G, and we see that a single central processor or a single cloud radio access network is no longer able to manage the large-scale interference. And therefore, in this case, we deploy several central processors, also multiple cloud radio access networks, so to say, where each central processor will manage its own associated resources. For example, its own set of base stations, as we can see here. And all this is done while utilizing a minimal communication overhead between the central processors. What we see here is that this allows for the distributed and scalable intelligence of the radio access network. This also allows for flexible distributed optimization of the overall system variables, all while maintaining a reasonable communication overhead between the clouds. Of course, this brings some issues, this architecture. For example, that we not only have one type of interference, now we have two. As we can see, for example, here, this is one cloud instance, right inside this is the next cloud instance, and between these clouds, we would have interference. What we also have additionally to this, a a problem that CRAN itself brings with it is the intra-cloud interference. And both need to be handled. Okay, a few more details on the network setup. Right-hand side, we keep the same figure and check some more details. First of all, we consider the downlink of a multi-cloud radio access network, where we have a number of C, central processors, and a number of B, base stations, which each have multiple antennas. Furthermore, we see that we assume that our network has a number of single antenna users, which is K. Previously, we have learned that what data sharing means. We utilize the data sharing fronthauling strategy and assume that the transmitters have the full channel state information available at them. From the communication part, we assume that we can manage physical layer and link layer resources. On the physical layer, that would mean we have beamforming vectors, which are referred to as W with subindices B and K. So that is the beamforming vector from a base station B to a user K. And we also have another beamforming vector W tilde, which refers to the beamforming vector from CPC to user K, whereas in CPC, all base stations of a central processor are included. Next up, we have the allocated data rates for each user, which is given in bit per second. On the link layer, we assume that we control the user-to-cloud association, which is referred to as Z, and the base station to user clustering, which we give the parameter T, telling us whether a user K is associated or clustered with the base station B. Now, to talk about energy efficiency and the motivation, we have heard the motivation by Ericsson to stop actually the increase of this energy curve that we saw. And now talking about the energy efficiency metric, we see that energy efficiency has two conflicting objectives. The optimal energy efficiency is reached by maximizing the data rate, but also minimizing the power consumption of our network. And to do this, we can balance the objectives as a fraction, where we can say that the energy efficiency, which is a metric given in bit per joule, is equal to the data rate given in bits per second divided by the power consumption in watt. Okay, so in more details, we now check the energy efficiency metric of the multi-cloud radio access network, and we want therefore to maximize the following expression. First of all, we have a sum over all the clouds that are part of our network, and within the sum we see that there is a fraction. That is, first hand side, on the upper side, we have a sum over all users and their respective data rates. In this case, a data rate between a user K and a cloud C would only have an allocated, so a value if this user is associated to the cloud C. Next up, we have the baseband processing power, which is also a sum over all users. This is an indicator function, and this is the squared second norm of the beamforming vector between cloud C and user K. In this case, this function tells us whether a user K is associated with a cloud C. And if so, then this will be a 1. And in that case, the processing power, the baseband processing power of that user will be added to the power consumption of that cloud. Next up, we have the transmit power. So here it's a sum over all base stations within the base station cluster of cloud C. This is the base station's transmit amplifier efficiency. This is a sum over all the users K. And these are the beamforming vectors between base station B and user K, which only will have a value in case users also is associated to a base station. And at last, we have fixed power, which is required for the circuitry and the cooling of the overall network. Now, of course, this maximization problem is subject to some constraints. In our case, we have a per base station maximum transmit power constraint, a per base station frontal capacity constraint, which is the link between the base station and the CP. Then we have achievable rate constraints per user. We have a so-called big M formulation per user and per base station. And this would actually tell us whether a user and a base station are connected or allocated to each other, assigned to each other. Then we have the user to cloud association constraint, and we say that some of our variables are binary. For example, the Z, which is actually the user to cloud association. A few more details on the problem. We show here the frontal constraint explicitly, which consists of a sum over all users k, and again, an indicator function of the beamforming vector between base station B and user k. And in case they are associated, so base station will serve a user k, this will have some value, and the indicator function will become 1, so that the rate of user k is contributing to the frontal link of base station B, which is limited by the maximum frontal capacity of base station B, FB. Okay. Next in line, we have the big M formulation, which makes sure that if a user k is associated with cloud C, then this will be a 1. The M is a big integer, and then we know that the beamforming vector between the base stations within the serving cluster, within the cluster C, so the cloud C, can serve actually this given user. And otherwise, if we check, for example, a user which is not associated to a cloud C, this will result in a 0, and this forces all of the beamforming vectors from all of that base station cluster of the C to not actually serve this user. Next one, here we see that a user may only be associated to one cloud. Here we see that cloud can serve only a maximum number of users. So this is limited, and that Z is a binary variable. Now, again, this problem is non-convex, mixed integer, and we first start with a generalized assignment problem to fix the user to cloud association. So here we see the first reformulation, which is we refer to as generalized assignment problem. In this case, we want to find the user to cloud association, Z, as an initial step, and we first characterize an energy efficiency-like utility function. So this utility function is trying to depict the benefit of assigning a user K to a CPC. So here we have the sum of all Cs, all clouds, the sum of all users, and then the association, ZCK. And this is an energy efficiency-like function. This is the utility function, we call it U. And it's the data rate of user K divided by the power consumption, so it's processing power, and actually it's transmit power. So this generalized assignment problem is then subject to, of course, the constraints we have previously mentioned. Now the benefit of doing this, so the energy efficiency-like utility function, the benefit is mainly dependent on two factors. First of all, it depends on the CPC to which a user K is assigned, and also the characteristic of this beamforming vector. So this is quite important for this generalized assignment problem. In this part of the gap generalized assignment problem, we fix the beamforming vectors to be maximum ratio transmitters, which are defined here. Now, this generalized assignment problem can be solved efficiently, for example, via distributed iterative auction algorithms, as can be seen, for example, in this reference. Okay, at this point, we will fix, based on the previous slide, the user-to-cloud association and end up with a new problem. We only now optimize the beamforming vectors and the allocated data rates. We have the same energy efficiency objective, which we want to maximize. And we end up with removing some of the constraints. So we keep only the frontal constraint and the big M formulation, whereas the Z is fixed. So this is also a convex constraint. Next up, how would we reformulate now? This is the L0 normalization, where we previously had discrete functions, discrete indicator functions. And these are now, based on this reference, replaced by fixed weight beta and the L0 norm of whatever was the argument of that indicator function. In this case, it was the squared L2 norm of the beamforming vectors. And yes, this is the reformulation. Now, these beta would be constant weights, which are updated to these rules. And this update will be done iteratively. So at this point, we have started to generate an iterative solution algorithm for the original optimization problem. Furthermore, instead of having the fixed weight times some norm of the beamforming vectors, we extend this L0 norm approximation and include a new slack variable for the relaxed norms, and we call it T. And now T replaces actually this fixed weight in the beamforming vectors, and we introduce thereby two additional new constraints, whereas the betas of this will be iteratively updated. What we can see now is that actually this function here works perfectly fine, and this function here is bilinear. So we have actually here, let's say, non-negative parameter, and also here a non-negative optimization parameter. Now, how do we solve the problem? Skipping some of the details here. First of all, we start by initialization of the general environment. What are the parameters of our network setup? Then we go on to solve the user-to-cloud association with the generalized SM problem, as we have discussed before. Afterwards, we update some auxiliary variables, the details of which will come at a later stage in this tutorial, and then solve the optimization problem at each cloud individually. That's one of the main points of the multi-cloud related network. In this case, we do the beamforming. We form base station clusters within each CP or CRAN, and also do the rate allocation. Afterwards, we update feasible fixed values, for example, the fixed weights we have seen on the previous slide. As I said, this is an iterative algorithm which is based on fractional programming, L0 normalization, and inner convex approximation, whereas some of these techniques we have discussed today, also previously, generalized SM problem and L0 normalization, but fractional programming and inner convex approximation will come at a later stage in the tutorial. As a last step here in the right-hand side figure is the information exchange between the cloud instances, which will also come at a later stage in the tutorial. Now, let's see some example simulations. This is an example setup. For example, here we have 4 clouds and base stations generated within the clouds and users generated within this whole area. And the clouds are separated as square areas here. Just as an example. Both base stations and users are randomly placed. Now, first of all, we want to check the energy efficiency versus the frontal capacity. The parameters we use are 4 clouds, 28 users, 14 base stations with 2 antennas each, processing power of 15 dBm and circuitry power of 38 dBm. Here we see, again, as I said, the energy efficiency in megabits per joule over the frontal capacity in megabits per second. Now we have multiple algorithms which we show the performance here. First of all, we start with the upper one. This is the centralized protocol. In that case, centralized means we will not have a separation between clouds. Rather, all base stations, all radio access network resources will be managed by one central CP instance. And this is the energy efficiency we can see for this framework. We see that for low frontal capacity, energy efficiency is around like above 40 megabits per joule. But if we increase this frontal capacity, which is one of the limiting factors in C-RAN and M multi-cloud radio access networks, we see that definitely the energy efficiency goes up to some point where we see that slowly a saturation will settle in. And this is mostly due to the limits of the interference between the base stations. As of course, with more frontal capacity, there's much more throughput going through the network and much more interference. Secondly, we have the proposed protocol, which is the distributed one. So meaning that there is an information exchange between the cloud components, but they are not directly connected, which is the much more practical and realistic setup. And this is the red dashed line here. And we can see that, especially in the beginning with low frontal capacity, the distributed protocol actually performs quite close to the centralized one, even though, of course, it has some drawbacks, especially if you go to the right-hand side of this plot. Still, to compare to a baseline scheme, we have a baseline scheme called fixed clustering. The fixed clustering takes some state-of-the-art clustering algorithm and actually, then also optimizes the energy efficiency over the frontal capacity, but with keeping the clustering fixed. And in this case, we see that both our centralized and distributed protocol that we have proposed here in this work are performing way better in terms of energy efficiency than this baseline fixed clustering scheme. Just as a takeaway, we see that there's a considerable gain of the dynamic clustering over the fixed clustering in this case. Now we want to check the energy efficiency versus the network density. And one additional reference scheme we add now is so-called distributed inner convex approximation, DICA, which is an algorithm that we will present on in the next part of the tutorial. But what we check is the energy efficiency over the network density. Network density is given in terms of base stations per square kilometer. And what we see is that both our algorithms are outperformed, especially in not so dense networks, by the DICA reference scheme. But what we see is that as the network becomes denser, actually the performance, for example, of the both distributed protocols, DICA distributed and our distributed one, they seem to converge. So they come closer. So that just shows us that A, on the one hand, the energy efficiency is increasing with increasing network density, but B, our algorithm is keeping up with some sophisticated state-of-the-art algorithm. And now, for the benefits of our proposed algorithm, is that if we check the normalized runtimes of these algorithms, we see that actually our proposed distributed protocol outperforms A, the centralized one, and B, the whole DICA algorithm itself, right? So we see on the left-hand side, we have a very close performance in terms of energy efficiency of distributed DICA and distributed proposed algorithm, but having more than 2 times lower runtimes, which is a significant advantage of the proposed protocol. Making our algorithm much more scalable in comparison to the centralized solution and to the comparison to the state-of-the-art benchmark. Now, some of the challenges we face with this specific multi-cloud radio access network architecture. of course, what we see here is that we have a congested frontal utilization, for example, during peak traffic times. Here is an illustration of this. We have the demand of, for example, for data, and we have the time. And what I want to show in this figure is that we have some current traffic plot, which is here, and it's strongly time varying. So we have some times where there's actually a lot of demand on data that wants to be transmitted through the radio access network. And usually what we see here is that this figure, they reserve a lot of bandwidth or a lot of resources to cover all of those peak traffic times. But that means in the low traffic times, we have a lot of waste, right? And yeah, this is a challenge. And one of the ideas to solve this is that we can cache actually often requested content at the base station or the edge of the network. In that case, we can try to minimize the data that goes through, for example, the frontal link, because some of the data is already there. It's already at the base station or at the edge. So we could cap some of this demand here because it just does not need to be transmitted through the network. Now the question is, do we want to cache at the central processor or at the base station? How is this impacting the energy efficiency objective? And this is what we find out in the next part. So let's check the architecture, cache-enabled multi-cloud radio access network. On the right-hand side, we see a cache-enabled CRAN. So we have central processor in the middle. We have all of the requestable files at its some cache at the cloud. But we see that some of the base stations, or all of the base stations, have some local cache available where they are able to cache often requested data directly on some of their servers. So we check edge caching multi-cloud radio access networks where we store popular content at the base stations to the edge. By that, we want to reduce the backhaul congestion on this frontal link and alleviate the frontal load, which is one of the bottlenecks we have in multi-cloud radio access networks. Furthermore, this is able to minimize content delivery time during, for example, as I previously mentioned, the peak traffic communication. However, this brings another challenge. Now we have a split of processing the user data either at the central processor or at the base station, right? Because if I want to serve a user based on some content I have at the cloud, I will do the processing of this user data. If you remember, that was the baseband processing at the cloud. But for example, now two base stations are caching the content of one user, and the user or the algorithm decides that both base stations will serve this user. Then the baseband processing needs to happen locally at both base stations. And this needs to be taken into account in the energy efficiency metric. Now to the network setup, again, we consider downlink MCRAN with CCPs, base stations, and casing antenna users. Interesting new fact here is we have a hybrid functional split so that we can either do the baseband processing globally at the CP or at the base station locally, depending on if we have a cache hit or not. This will show a trade-off between the computation costs and the frontal costs. Communication architecture-wise, we still have beamforming vectors W, allocated data rates R, user-to-cloud association Z, and base station to user clustering. Whereas this is a more interesting thing now. This TKB refers to, of course, again, if a user K is clustered with a base station B, so base station serves user. But there's also the T tilde, which means basically the same, only that the left one is for no cache hit. So we do the serving just as in the previous algorithm via the cloud. But the T tilde means that actually the content is cached at this base station and the algorithm decided to utilize the local processing at this base station. Now, let's check the energy efficiency metric. It becomes much more complex now. We still want to maximize the energy efficiency. We still have some over all clouds, and we still have up here the data rate. But what comes to this additionally is the transfer power, which is a bit more complex now because we have beamforming vector between base station B of a cluster C to a user K, and the same also for the cached content. Then we have operational power again, which is called PC per processing. And we have the baseband processing power, which is a much more complex function now. Let's check the following. G, energy efficiency of a cloud C. First is, if we decide that user K is served by base station B, but the data of this user will be processed at the cloud itself, then we have some cost in terms of using the front haul link to transmit actually the processed data from the central processor to the base station itself. Then we have processing at the base station, which again, I described this in the beginning, will have some costs. If we have a cache hit and the algorithm decides, okay, we process the data at the base station, this will cost, right, in terms of energy consumption. At last, if there was no cache hit and we decide to do the processing at the central processor, then we invest this same cost actually at the CP. Now, the interesting thing here is that on cache hit, we will not activate the front haul link. So this cost goes away, and we will not process at the CP. This cost goes away, but we might process at multiple base stations. So this could be sum of multiple base stations. In case we decide to process at the central processor, we first of all invest the processing power there, and then activate the front haul link to each serving base station. So we can see that there definitely will be some trade-offs between doing both or doing this, depending on the situation. Again, we see the optimization problem subject to maximum transfer power constraint per base station, front haul capacity constraint per base station, achievable rate constraint per user, a cache hit and miss constraint, a big M formulation, user to cloud association, binary variables. And this all while maximizing the energy efficiency with some of the variables being beamforming vectors, user to cloud association, data rates, and base station clustering with multiple types of cluster. Now, first of all, again, we start with a generalized assignment problem to alleviate the need to optimize this user to cloud association. So this will go away, and we will have a fixed user to cloud association. Some of the details of this optimization problem can be seen here. Especially interesting is the cache hit or miss constraint, where I have described that this W tilde is only activated on a cache hit. In this case, the W tilde will be 0 if a user belongs to a class of cache miss users. In that case, that means the user data is not cached at any base station. And otherwise, of course, this constraint will not be valid. If he has a cache hit, then there might be, the beamforming vector could become active. Now the front haul constraint, again, we have the indicator function telling us whether front haul link will be used for transmitting user data. And we have another factor here, which refers to actually if there was a cache hit or no. Because if there is a cache hit, then this variable, fk being the file that a user k requested, will be 1 for that specific base station B. So there's 1 minus 1, and will be 0. And that case means this is 0, and we also know that on a cache hit, this base station will not serve the user with global processing, so this will also be 0. And then the rate of this user will not contribute to the front haul link. Right. Okay. Now, skipping some of the solution parts. Again, we do the user to cloud association in the beginning based on generalized assignment problem. Then we manage the beamforming, base stations to central processor access. And that means whether we have caching or no, the base station clusters, and the rate allocation by the similar algorithm than we had previously mentioned. So it's an iterative algorithm which is based on fractional programming, L0 normalization, and inner convex approximation. whereas these parts will come later in the tutorial. And this also is implemented in a distributed way, where the solution is done at each cloud, and then we have some information exchange. Okay, a few more details. How can we solve the objective function, which is fractional? For this, we utilize fractional programming. Especially here, we utilize the Dinkelbach algorithm. And here, just to show the general idea, this is the original problem. We want to maximize this fraction, or a sum of all these fractions. And what the Dinkelbach does is it tries to iteratively search for a unique solution to a new problem, an auxiliary problem. And the auxiliary problem becomes like this. We have made some colors to the ease of access. So we still have the sum of all C's, of all clouds. Then we have the sum over all rates minus auxiliary variable lambda. And then we have the whole denominator here at this lambda. What we can see is that this new problem is not a fraction. It's not a fractional nature anymore, but we have a new parameter lambda, which in this case for the Dinkelbach algorithm will be updated iteratively, yielding an iterative optimization approach. Okay, so let's check some results. Now we want to check the energy efficiency versus the parameter frontal capacity. And for this, on the left-hand side, we plot the energy efficiency versus the frontal capacity, and do that actually for two different processing powers. Left-hand side is the lower processing power of 10 dBm. Right-hand side, we would have a processing power of 25 dBm. So first observation is we have some comparisons here. We have a no caching, which is yellow. That means the cache size is empty. We cannot cache at the base station baseline. And for each color, we increase the cache size at the base station by 10%, up to a 50% of cache size. Now we see that over the frontal capacity, first of all, the energy efficiency is rising, which is a result we had previously. But also what we see is that a bigger cache results in more energy efficiency, which is a result, one of the good results that this framework brings with it. Interestingly, on the right-hand side, we have more processing power. This gain of having a bigger cache size actually decreases. Of course, in general, overall, the energy efficiency is decreasing because we have now more power to spend. But at some point, even we see that caching does not even have a real gain in comparison to utilizing the frontal link. Because at some point, it's just better the algorithm would decide to only use the frontal link and never process user data locally, especially as the processing in this case on the right-hand side is quite expensive. Right, so we see that edge caching, the edge caching gain decreases with large frontal capacity and also with high processing power. But let's say realistic systems, we would rather say the frontal capacity is rather limited, and of course, yes, processing power is usually high. Next thing we check is the energy efficiency versus the file availability per cloud. In this case, the idea was that we have a multi-cloud system. There are multiple CPs. And here, not every CP has access to the whole library of requestable files. In that case, we see that actually both centralized and distributed algorithms are rising in energy efficiency as more files would be available per cloud, right? And the upper baseline is that what we also have shown previously, that at each cloud, all of the files are available. This is the upper baseline. And yeah, interestingly, it's clear that that if there are less files available in the cloud, the energy efficiency is decreasing. One of the nice results of this is that we see that there seems to be a constant gap between the centralized and distributed implementation, whereas, of course, I think we have previously discussed, the distributed implementation is much more scalable. in comparison to the centralized one, and also in terms of runtime. Yes, takeaway, we see that cloud caching has a significant impact on the energy efficiency performance in this case. Now let's talk about the challenges and limitations of the multi-cloud radio access networks. First of all, MC RANs encounter problems such as poor service quality, especially at cell edges. This comes due to the fact that at the cell edges, often the received signal power is weak. And furthermore, the interference is quite strong because we're at the cell edge and there comes the next cell, so the next CP. That means service quality is quite poor, can be quite poor. Also, the current framework is only talking about communication resources. We have not talked about something like computing resources, for example. And those two things limit actually the MC RAN's application in many 6G use cases, which are often dependent on the convergence of communication and computation, and are also limited by poor service quality at the cell edges. Resilience of MC RANs. So previously we had the C RANs, and already there we had virtualized and flexible network functions at the CPs, making already the network quite resilient. And in the MC RAN part, we also noticed that now we alleviate a single point of failure. We have multiple clouds available. If a cloud fails, for example, some components of the cloud fail or the whole cloud fails for some reason, connection is maybe lost or something, then the network, the overall network, has still available different other clouds. And in that case, the users of a failed cloud might be somehow associated to the remaining clouds to at least restore some of the service level. Of course, this architecture is quite unflexible in terms of access. So we have only one access mechanism. Computing is, not considered here. And of course, what this architecture cannot do is it cannot really account for varying quality of service needs, because we only have, let's say, a single tier architecture. We have multiple clusters, multiple cloud radio access networks, but each CRAN has the same type of CP, right? So we cannot really, this is quite unflexible. And yes, to tackle this, next we talk about hybrid networks and go into that perspective. But for now, I'm available for questions, for example, via the chat. And thank you for your attention, and I will give the word then afterwards to my colleagues.